This is now our third in a series of videos on Riemann sums for estimating area under a curve. In our previous video, we computed Riemann sums numerically using a table of values. That's great for a fixed set of data. But here, we can go much further if we start with a really simple function, and then we can compute the Riemann sum for every value of n. And then that allows us to take the limit as n goes to infinity. And that'll give us the integral, which is the actual area under the curve. So we'll give two examples of this. And the first is just the line y equals x. For simplicity, we'll take the interval 0 to b, the area under the curve. Well, we know that that's a triangle with base b and height b. So we already know what the area is. So this will be a good test case to see if the integral gives us what we expect. We start with n subintervals of width delta x equals b over n. Our formula for xi, that's just I times delta x. It comes out really simple. It's just b times I over n. So here is the right Riemann sum. It's simply the sum of the xi's times delta x, which is this expression after we substitute in our delta x and our xi's. Now we can factor out b squared over n squared times what's left is 1 plus 2 plus 3 plus plus n. Now this is where we're going to pull a rabbit out of a hat. There's a formula for this sum of the numbers 1 plus 2 plus 3 plus plus n. And I will say something about this, but I'll postpone it to the end of the video. There's a postscript about this. So if you don't care to know, then you can skip the postscript. But just take it as given for the moment that 1 plus 2 plus 3 plus plus n is this formula. And now I want to rewrite that, simplify it in a way that allows me to be able to take the limit as n goes to infinity. And when I let n go to infinity, I get the integral. So the integral of x from 0 to b, that's the area under the curve, is this limit as n goes to infinity, the limit of the Riemann sum. And you know how to take this limit. It's elementary, and the answer is just b squared over 2, which you should already know. You can use the formula for the area of a triangle, or you can just say, well, it's half of a b by b square. So same thing, that'll give you this answer. Now, very good, but let's look at something that you cannot do with just high school geometry formulas. This is the area under a parabola. And this is where Riemann sums really pull their weight. So I'm going to take the function f of x equals x squared. Again, the interval 0 to b, as before, n subintervals of width delta x equals b over n. Just like last time, xi is bi over n. And then we get the right Riemann sum, which is very similar to the previous formula we worked out. But this time, we have all the xi's are squared. And then we pull out the common factor delta x. And when you substitute in the delta x and the xi's, this is what you get. And now you can factor out b cubed over n cubed. What's left? Now here's a difference. Instead of 1 plus 2 plus 3 and so on, we have 1 squared plus 2 squared plus 3 squared plus plus n squared. Now there's, again, a formula for this. So we pull another rabbit out of the hat. Now, it'd be nice to talk about this formula too, but let's just say it's outside our mission parameters. So we're going to skip the diversion, however interesting it might be. And this formula, which we take for granted, now I just rewrite it, simplify it. You could say so that it's in a form you can easily take the limit. And when we take the limit, then we get the integral. The integral from 0 to b of x squared is the area under the curve, the area under the parabola from 0 to b. It's this limit, and you know how to compute that, and the answer is b cubed over 3. So these examples show how the integral is defined as the limit of Riemann sums. We often have need of Riemann sums to approximate integrals, but if you really want to do this job to compute the Riemann sum and then take the limit as n goes to infinity, it's going to be a lot of work. You're going to be pulling a lot of rabbits out of hats with fancy identities and formulas for sums like I did here. So instead of doing this method every time, we're going to find a better way to compute integrals using antiderivatives. That's coming up very soon, but we can catch a glimpse of what's in store by looking at these two formulas. These are the ones we just worked out, the area under a line, the area under a parabola. And you should compare this with a couple of antiderivatives that you should know by now, and you should see an obvious similarity here. And the explanation is soon coming, but it's all wrapped up in the fundamental theorem of calculus. So we'll save that for a future video, which is coming very soon to a screen near you. Now, here is that postscript that I promised. We're interested in this sum, which I'll call S. It's 1 plus 2 plus 3 plus plus all the numbers up to n. And of course, if you list the same numbers in reverse order and add them again, you should get the same answer. It's again S. But now I'm going to add these two formulas together. And on the left side, I'm just going to get 2s. But if you look at each column adds up to n plus 1. And there are n columns. So that means that 2s is actually equal to n times n plus 1. And then you just divide both sides by 2. And you get s is the formula that I used earlier in the video. So there's actually a story, a very popular story with this, about the great mathematician Gauss, who was, at the time of this story, was a schoolboy, and the teacher gave the students a task which was intended to keep them all really busy so the teacher could read his book or something. And they were supposed to add up all the numbers from 1 to 100. And Gauss, who at that time was only 7 years old, immediately wrote down 5,050 on his slate and handed it to the teacher, much to his annoyance, of course. Apparently nobody else in the room, not even the teacher, knew the trick that I just showed you for adding up the numbers 1 up to 100 or 1 up to n.